Actually, most of them follow the power law distribution. But then why does this result happen?
There are two main reasons to explain the distribution. First reason comes from the variability of the network. Some individuals can join the network or drop out of the network. In other words, the number of nodes contributed to the network is not fixed. For example, the documents in the World Wide Web make a huge network. Suppose that you have your own personal web page. Then you can add a new document to your web page or erase some old ones. Also, that attachment is not uniform. A node with more links will be linked with high probability. In short, the rich get richer. Consider the case when you try to link your web page to another. What website would you want to link to? You try to choose the well-known websites. In fact, this distribution makes our network more efficient. Also, the network with this distribution is more robust under random errors, but very valuable to intentional attacks.
This real-world network model was first developed by Hungarian scientist Albert Lazar. His model is being used by many scientists to try to solve the present problems happening around us. The academic control strategy is one of the well-known representatives of its kind of works. For many ages, people have been trying hard to stop the spread of diseases, but attempts have remained futile. Using this model, scientists can easily find out how the diseases are spread in a network and contain them. Imagine a graph representing a society. If the disease starts to spread, how can we stop this? One easy way to choose several random people and protect them against the diseases. This method we call the uniform immunization strategy. But it has been figured out that this strategy is useless for highly contagious virus, and in fact it just has scientific effect for our society. It's because of the distribution of the social network. The existence of hubs makes these kinds of methods ineffective. Of course, now we have to try to find out the super spreader in the networks and isolate them from the society. And we call this method the target immunization strategy. Then how can we find out who the hubs are? Unless we examine the whole structure of the network, it cannot be possible. But some scientists overcome the difficulty and give a new strategy which is effective even if they have little information about the structure of the network. In comparison with the uniform immunization strategy, for this method, first we have to choose a random person in a network, and then we protect one of his connected persons who is also randomly chosen. That person has high probability to turn out to be the super spreader in this network, and we call this strategy the random acquaintance strategy. In KAIST, there is a physics department which is keen on researching on complex systems. Professor Zhong, who is in the department, has conducted numerous researches on the application of complex systems. His research papers are published under Nature Journal, and it can be found in KAIST Digital Science Library. As we look through the journal, we find that his research papers range from the Internet to protein network. Currently, he is interested in applying complex systems in the following areas, such as bioinformatics, network modeling, self-organized pattern formation, and economics. One of the hot topics that have caught many scientists' attention is the network biology. Using complex systems, network biology involves the mapping of specific biological molecules into the metabolic pathway. Professor Zhong is currently developing a model which will represent the actual metabolic pathway. Scientists can use it to analyze the metabolic pathway and to understand how it affects the metabolism of an organism. By doing so, scientists can know how to block certain harmful metabolic pathways, which will help to improve the production of useful products. This is known as metabolic engineering. In the coming future, researches in this area will be extended to human metabolic pathway. The potential benefit is that one day, network biology will be used to cure certain human diseases by developing drugs to control the target metabolic pathway. Since complex system is in the early stage of research, scientists in KAIST, including Professor Zhong, is still trying to find out more about complex systems. More researches are being carried out by collaborating with different professors in KAIST to apply the complex system. In the future, Professor Zhong is planning to set up an institution where it will conduct further researches on complex systems.